Welcome back. As I've said several times throughout the semester, this chapter is another chapter that doesn't really introduce any new physics. There's no new physics here. We're just taking results that we're already familiar with, massaging them mathematically, and putting them into a different form that's useful for solving problems. So this chapter introduces your next conservation principle. We've already looked at the conservation of mechanical energy for situations where there's no non-conservative forces acting. Now we're going to look at a different conserved quantity. And our starting point is to examine an isolated interaction between two masses. So the simplest way to think about it would be two clumps of mass colliding. So here's a clump of mass colliding into another clump of mass. And you know what, this one looks like it's not being pushed, so maybe I should draw them both a little squished. Right, so these were previously moving quickly, and now they've smashed together. I'll call this mass A and mass B. And these arrows just indicate their velocities prior to the collision. But if I'm interested in talking about the forces, let me make this a little bigger. Well, I said isolated collision, so the idea is there's no forces acting on either of these masses except for their interaction force. So I'll use this arrow to represent mass B pushing on mass A. This is the force of B pushing on A. It's directed that way. And Newton's third law tells us that the force of A pushing on B would have to be equal in length but opposite in direction. Force of A on B. Now, if these really were separated, moving quickly, and then they squish together, presumably, as they're colliding, these vectors would get longer and longer, and then they would get shorter and shorter until the masses have separated. So these forces are changing in time, but the idea is at any moment in time, the two vectors are equal in length and opposite in direction. And our starting point will be this, Newton's third law. We'll say that the force of A on B is the negative of the force of B on A. And before we look at the math, why don't we just have some examples in our head? An isolated collision here could be the collision between two billiard balls. That's a good example. It could be a car crash that we're talking about.
That is not bad. That is almost dead on.
Oh, the wheel moves on the left-hand side one.
Now, it's true that there are other forces on these vehicles. There's the ground pushing up, there's gravity pulling down, but you can imagine that during the collision, the force that these cars exert on each other is probably much greater than either of those other forces. But try to keep in mind that it doesn't have to be a collision in the normal sense. So it doesn't have to involve repulsive forces. If you try to collide two baseballs that are going to push against each other, the force between the objects could actually be an attractive one. So here's an example of a gravitational collision, if you were. Think of this as a massive star. Here is a planet like Jupiter. And over here, this small turquoise ball would be like a man-made satellite that's been launched into outer space. And you're going to see in a moment an animation of what they call this, well, some people call slingshot effect or a gravity assist. This thing will be accelerated to a greater speed by its gravitational interaction with Jupiter. So just wait a few seconds and train your eye on the interaction between these two. Again, watch the turquoise ball. In a moment, it's going to interact with what I'm calling Jupiter right here. So during the time that they were passing each other, yes, there was still an attraction from the star, but if you set that aside and just focus on the interaction between the two, it was a collision in a sense. They weren't repelling each other, but they were still influencing each other via their mutual gravitation, and there would have been an exchange of what we call momentum. That's what we're getting to in just a moment here. So we've started with Newton's third law. And I talked a little bit about this early in the semester. Newton's third law is really not, it's not a law that never gets broken, because it's easy to imagine an interaction between two charged particles that disobeys Newton's third law. So a proton and a proton acting at a distance from each other, the forces that they exert on each other are not necessarily equal and opposite vectors. So that's kind of a profound thing to talk about. It's not usually presented in these classes because it's a challenging concept, but fortunately it doesn't matter, because I believe Newton's third law is almost always valid if you're talking about contact forces, two objects that are pushing on each other because they're actually in contact. And that's pretty much all the forces we talk about in 3A, with the exception of gravity. Okay, so now we invoke Newton's second law. If this is an isolated system, then this is the only force on mass A. The force that B exerts on A is the net force on mass A, because there are no other forces. And that means that it's the time, or it's mass times the acceleration of mass A. So over here I'm going to substitute. Since this is the net force on mass A, it should be mass A times mass A's acceleration. So the acceleration of mass A. And same thing over here. The force of A on B, well, this is the only force on mass B, hence it's the net force on mass B. So that should be equal to mass B times the acceleration of mass B. I'm using Newton's second law. Now for the next step, I'll remind you that acceleration is the time derivative of velocity. So instead of writing A for acceleration, I'll write dv dt. Mass B's acceleration would be the time derivative of mass B's velocity. So this is ddt of v sub b. Over here, the acceleration of mass A, capital A for mass A, would be the time derivative of mass A's velocity. So ddt of v sub A. So it may not look like it, but this is Newton's third law for this particular interaction. Again, these are the only forces on the respective masses, hence they are the net forces, and that's why we can use Newton's second law, which got us to here. Okay, now my next step, I think I'll rewrite this at the top of another page, and this time I'll leave some space here, and you'll see why in a moment. Mass B, ddt of mass B's velocity. Okay, our next step is to integrate. Now you recall in chapter 10, we took F equals ma, and we integrated with respect to position to get the work kinetic energy equation. This time, we're not going to integrate with respect to position. Since I've got this differential dt down here, I want to integrate over time. So let's do a definite time integral. And if we still want to make this an equality, of course, we have to integrate between the same two limits on both sides. So you're all familiar with, in algebra, you can, if you've got two things that are equal, as long as you add the same quantity to both sides, they're still equal. As long as you divide them by the same quantity, they're still equal. Well, here what I'm doing is integrating both quantities with respect to the same variable and between the same two times. And instead of t initial and t final, I will call them t1 and t2. You could use any subscripts that make sense. And now let's think, what's happening here? Well, you recall that a mass, or excuse me, a constant, and we're imagining that these masses are constant. A constant can just be pulled out in front of an integral, so I can ignore that for the time being. And how do you find the antiderivative of the derivative of velocity? We've got a vector that we've differentiated with respect to time, and then we've integrated with respect to time. Well, maybe you remember the integral of, let's see here, the integral of f dx is equal to f of x plus some constant. I'm sorry, this is for another class, let's ignore that. Where big F I'm sorry, where the derivative of big F with respect to x is lowercase f, right? If you took the derivative of big F, you would get back to the function that we're integrating. So this is called the antiderivative. This is an indefinite integral. I haven't specified limits. When you do specify the limits, if I said from x1 to x2, well, this would become f of x2 minus f of x1, and that constant goes away. And the same thing is happening here. So what is the integral of the derivative of v? That would just be v. It's like the two operations undo each other, right? First we differentiate with respect to time, then we integrate with respect to time, and we're just back to whatever we started with, which in this case is the velocity vector. So this is going to be vb at time 2. So I've evaluated the antiderivative. The antiderivative of the derivative is just v. Evaluate that at time 2. I'm abbreviating that vb2 minus the antiderivative evaluated at time 1. And I still need that mass out front, right? Over here, by the same logic, the integral of the derivative of velocity is velocity. Evaluate at your upper and lower limits, and that would be VA2 minus VA1. And now let's move things around. Everything with the subscript 2, I will place on one side of the equation, and everything with the subscript 1, I will place on the other side. So let me move all the 1 step over here and the 2 step over here, and here's what I find. MAVA2 plus MBVB2 equals MAVA1 plus MBVB1. Let's unpack this equation. What's going on here? Well, we know that both of these velocities are changing. As these two masses collide, their velocities are switching directions. In fact, they may be going off in totally different directions, and the speeds are changing, so everything about these velocities could be changing. But what's interesting is that if you take each mass, multiply by its velocity after the collision, because I'm imagining that the 2 times here are before they collide and after they collide, but nothing about this thought process here requires that we choose those particular times. I really could pick any 2 times during the collision. But at those 2 times, for the final time, take each mass, multiply by its velocity at the second time, and then add those 2 resulting vectors up, because these are both vectors, right? If you take a vector and multiply by a scalar, it's just another vector. You've just stretched it out or shrunk it by some amount. So even though the velocities are changing, when you take the mass, multiply by the velocity, and then add those 2 up, that quantity is the same at time 2 as it was at time 1. And that's very interesting, because that's not common sense. We're not born knowing that, or we don't go through life not having studied physics and knowing that there's this vector quantity that should stay the same at all times during a collision. Because remember, these could be any 2 times. So I could just say, in other words, MAVA plus MBVB is some constant. Since it's the same evaluated at any 2 times, then it's the same at all times. So let's just call that total vector quantity a constant. That is interesting, because it's clearly not the velocity that's constant. We can see each car changing velocity in a car crash, or each billiard ball. We can see a football player's velocity change during a collision. What's not so obvious is that there is a vector we can look for that does not change during the collision. That vector is calculated by taking each mass, multiplying by its respective velocity, and then adding all that up. So some of you have seen this before. You know where we're going. We call this the momentum of mass A and the momentum of mass B. And we've just discovered that in an isolated collision, right, the assumption we made was F external. There's no outside forces. If the only forces are internal, it seems that the total momentum is unchanged. Each momentum individually is changing. Of course, if mass A's velocity switches direction, then so does its momentum, because momentum is just proportional to velocity. Each individual momentum is changing, but the total momentum is not. I want to repeat that one more time. Each individual momentum may be changing, but the momentum of the whole system does not change. And that is really because there's no external force. So I want to explore that point a little further. Let's apply Newton's second law. Second law for a single particle. First, let's define, well, I'll go through this in the normal sequence, or with the normal sequence of steps here. We know that the net force on a particle is the particle's mass times its acceleration. But we can rewrite acceleration as the time derivative of velocity. And then let's do this. Let's bring the mass inside the derivative symbol. Because again, from calculus, we know that if this is a constant, we can just pull it out front. I'm doing the opposite. I'm putting it back in. Well, we've just defined this quantity now. We're going to call mass times velocity momentum. So I could write this as F equals d dt of, and for whatever reason, everybody uses the letter P for this vector quantity. So force is the time derivative of momentum. This is an equation you do want to memorize. Everybody knows F equals ma. This is really a better way to write Newton's second law. It's even more general because it includes situations in which the mass might be changing. And it's very intuitive. If you want to change something's momentum, you have to apply a force. And the greater the force you apply, the greater the rate at which its momentum is changing. So let me continue with this equation. Force is the time derivative of momentum. If the net force on this particle is 0, if the left side is 0, then the right side must also be 0. So if you're not applying a force to something, its time derivative, or the rate of change of its momentum, should be zero. That's just another way of saying that the momentum is constant, right? If you're saying that something's rate of change is 0, what you're saying is that it's not changing, or it's constant, or it's conserved. That's the fancy word that people like to use in physics. So let me summarize the steps again. If you look at a single particle, you can rewrite F equals ma in this form. Force is the time derivative of momentum. And then it's very easy to recognize that no force implies that the momentum is not changing. That's for a single particle. What I did originally was look at a system of 2 particles. And yes, there are forces between the particles, but I argued, or I assumed, that there were no outside forces. And we arrive at the same result in that case. Even though the constituent momenta, that's plural for momentum, the constituent momenta may be changing. Each of these velocities could switch directions and lengths. The total momentum is still not changing. So it's like I've applied this result to the total system of the 2 masses. Okay, let's go back and repeat this integration one more time, because it's helpful to see it done in a variety of ways. And then we'll be ready to actually solve some problems with this new conservation principle. So let me go back to this picture again. And this time I'm going to use our new way of writing Newton's second law. So FAB, that's the force that A exerts on B. That's this force. Well, that's the only force on mass B. And we know that that means it's ma for mass B. But I've decided to write that as the time derivative of mass B's momentum. See that? This is the net force on mass B, because by assumption, there are no other forces on mass B. That should be the rate of change of mass B's momentum. Similarly, the force of B on A, well, this is the only force and hence the net force on mass A. That should be the time derivative of mass A's momentum. So I'm starting with Newton's second law, but then I'm going to invoke Newton's third law again. I'll say, but these 2 force vectors are equal and opposite. Contact forces can be, or contact interactions can be described by a pair of equal and opposite force vectors. So I will take these 2 now, set them equal to each other with the minus sign. And In a math class, this might be faux pas, but I'm going to regard these as fractions. We've got a numerator and a denominator. Since they both have a dt, let's just multiply on both sides by dt, if you want to do it that way, times dt. And then we're left with dp is the negative, got the wrong subscript, dp sub b is the negative of dp sub a. And that is really the crux of what this is all about. I'm going to do a couple more things with this, but this is a nice way to think about the interaction between these two objects. Because the only forces involved are the forces between the two, those internal forces, there's no outside forces, then over some infinitesimal time interval, remember how much time is that? Well, it's no time, but you can think of it like a nanosecond or a picosecond. Over a tiny time interval, whatever change in momentum is experienced by mass B, that's equal and opposite to the change in momentum experienced by mass A. It's such a basic idea. It's actually kind of intuitive, isn't it? Like if two cars are crashing, if this one's slowing down, then this one perhaps is speeding up in the other direction. The vector changes in their momenta are equal and opposite. And this is actually a decent starting place for a lot of problems. But let's make this a little easier conceptually and integrate that. So dp sub b is equal to the negative of dp sub a. Oops. How's about I integrate that on both sides with respect to, well, I was about to add a dt, but I don't need a dt because this is already a differential. So this, this is where maybe you're not accustomed to see these steps done with the math, but I need limits if I want to make this a definite integral. Since I'm integrating with respect to mass B's momentum, my lower limit would be the momentum of mass B at time 1 to the momentum of mass B at time 2. I need these limits to correspond to these limits. Well, at time 1, this is mass B's momentum. At time 1, this is mass A's momentum. And maybe you're thinking, wait a minute, how do you integrate a vector? Well, really, we're integrating 3 different functions. We're integrating a function along the x, y, and z axes. This is just a compact way of writing the whole thing. Okay, and if you're further confused by this, it's like this. If you were integrating dx, wouldn't you have to go from like x1 to x2? What's the antiderivative here? Well, you're actually integrating the function 1 with respect to x, and the antiderivative is x from x1 to x2. So you'd write it like that. That's exactly what we're doing here. So what's the antiderivative of dp? It would just be p, and then evaluate at your upper and lower limits. So what I really have here is pb2 minus pb1 equals the negative of, again, the antiderivative of p sub a, of dp sub a is p sub a, pa2 minus pa1. Well, can't we just call this delta p sub b? This is mass B's final momentum minus mass B's initial momentum. That would just be the change in mass B's momentum. And that's got to be the negative of the change in mass A's momentum. So that might be a better way to express what we're talking about. But do you see how that's really no different from what I had just written? This is the differential form of that same statement. This is the integrated form. So it's understood, this is the change in momentum over some infinitesimal time interval. Once you integrate between 2 times that are separated by any amount, you get the same result, but this could be over any time interval. So as long as it's 2 isolated things interacting, it doesn't matter if that collision takes a millisecond or 5 seconds or several hours in the case of the satellite moving past a planet. As long as it's an isolated interaction, the total change in one object's momentum will be the negative of the total change in the other object's momentum. There's no new physics here. Basically, this comes down to Newton's third law, right? This result follows from the idea that the forces between the objects at any time are equal and opposite. Okay, so no new physics. It's a different way of presenting it, and it's very useful for solving certain problems. So your book does not talk about energy conservation in this way. They write the equation a slightly different way, but I find that this is a really good way conceptually to start a lot of problems. Here's the other way you could write this though. You could just move this to the other side. This would be delta PB plus delta PA is 0. Well, this is final minus initial, this is final minus initial. So in a sense, I could factor out the delta sign, PB plus PA equals 0. It's the same thing, right? This would be PB final, or yeah, PB plus PA final minus PB plus PA initial. You'd wind up with the same expression that you have here if you actually wrote out, final minus initial. What should we call this? Well, since we've only got 2 objects in our system, mass A and B, if you add up their momenta, that should be the total momentum. So I'm just going to call that capital P. Hopefully you can tell the difference between the lowercase p and the capital P. And I don't need a subscript because it's the total momentum. So I'll say that's defined as P total. Okay, so in other words, the change in total momentum is 0. That's another way to think about this whole concept. In an isolated interaction, if it's 2 planets colliding and there's nothing else influencing them, or 2 billiard balls and you don't have to worry about the forces from the pool table or anything else, then the total momentum of the system does not change. That's what this equation says. The individual momenta may be changing. Each billiard ball is going to go off in some different direction after the collision. So those individual momenta change, but the total momentum does not. And saying delta P equals 0, well, that's the same as saying that the total momentum at time 2 minus the total momentum at time 1 is 0. Or you could say the total momentum at time 2 is the same as the total momentum at time 1. These are all equivalent ways to think about it. And then here you can break this up into the parts. We've got the total momentum at time 2 would be the momentum of object A at time 2 plus the momentum of object B at time 2. And the total momentum at time 1 would be the momentum of mass A at time 1 plus the momentum of mass B at time 1. So this is how your book generally starts problems. And I've already done that, right? Didn't we? The first time I went through all of this, this is the equation that I ended up with. It was right here. See the comparison here? This is PA2. This is PB2, PA1, etc. Okay? So there's a bunch of different ways to write it. There's a bunch of different ways to think about it, but they're all equivalent. So you pick the one that makes the most sense to you. And I think whenever I can, I like to use a statement about the deltas individually. I'm looking for it. Yeah, I like thinking about it this way, that whatever momentum change mass B experiences, mass A will experience the opposite change in momentum. So the best way to get a feel for this is to do some problems. Here is an easy one from your homework. This is number 28. There's no difficulty here in this problem. Just straight up conservation of energy, of momentum. Or I should say application of momentum conservation. You've got a kid on a skateboard. I say kid because we're told that Dan is his name. Dan is only 50 kilograms in mass, and he's riding a skateboard that's 5 kilograms in mass. And they're going along at 4 meters per second. That's about 10 miles per hour. That seems reasonable. And then for whatever reason, Dan kicks his skateboard forward, and presumably he's going to fly backwards. Well, not necessarily backwards compared to the ground, but backwards with respect to the skateboard. He's going to slow down at the very least. And you can think of that in terms of forces. If the skateboard sped up from 4 to 8 meters per second, then there must have been a force on the skateboard that points to the right. And that force would come from Dan's feet. Via friction, Dan would push on the skateboard to the right. And that means that the skateboard would be pushing to the left on Dan. So we expect Dan to slow down from 4 meters per second to some other number. So I really shouldn't have written this backwards. It's possible to launch yourself backwards, but you'd have to kick this thing really hard. So most likely he just slowed down. it's more than likely that his velocity is still forward with respect to the ground, but that it's now less than 4 meters per second. And we can easily solve this problem using momentum conservation. Before I do that, let's think about things intuitively here. Do you see how his mass is 10 times the mass of the skateboard? So I think what that tells us is that his change in velocity will be 1/10 the change in velocity of the skateboard. It seems reasonable, right? Since he's 10 times as massive, he should experience 1/10 the change in velocity. Well, the change in velocity for the skateboard was +4. It sped up from 4 to 8. So what's 1/10 of 4? That would be 0.4. I think he's going to slow down by 0.4 meters per second, which would bring his speed from 4 meters per second down to 3.6. Well, let's look at the math to actually find out. So I don't usually do this, but I guess I'll use a keyword from your book. We're going to model this as an isolated collision. So we'll pretend like there are no external forces. Now, really, momentum is conserved along a single axis at a time. I want you to remember that the total momentum at time 1 is the total momentum at time 2. In a two-dimensional problem, this is really two simultaneous statements. We're saying that the momentum in the x direction total is the same as the momentum in the x direction total at the end. So there are two separate statements about conserved quantities here. And you can never mix the two. You would never want to put x momenta into your y equation, for the same reason that you wouldn't put y forces into your F equals ma equation along the x-axis. You just don't mix the two. Well, this problem is really one-dimensional because we're only looking at motion in this direction. So if we want to argue that the momentum in the x direction is conserved, we have to be able to say that there are no outside x forces. Yes, it's true that Dan pushes to the right on the skateboard and the skateboard pushes to the left on Dan, but those are internal forces. Are there any outside forces in the x direction? Well, realistically, the entire time that he's rolling, there's a little bit of rolling friction between the ground and the skateboard. That would count as an outside force. If your system is Dan plus the skateboard, then there is an outside force called friction in the x direction. And there's also some air drag. But the idea is that those two forces are very small compared to the contact force between his feet and the skateboard. That's the whole point of a skateboard, right? To have as little friction as possible, as little rolling friction as possible between the wheels and the ground. You want to have good bearings inside the wheels and good rigid wheels that don't experience a lot of rolling friction. And air drag, how much air drag is there really at typical skateboard speeds? So we're neglecting those forces and pretending that this is an isolated system. And in that case, we can apply conservation of momentum. So I'm going to use my favorite starting point, which is to say that during this collision or interaction between Dan and the skateboard, whatever change in momentum is suffered by Dan will be the opposite of the momentum change suffered by the skateboard. I like to call this the Newton's third law version of conservation of momentum, equal and opposite. And since P is equal to mv for any particular mass, delta P would be mv final minus mv initial, factor out the m, and it's m delta v. So if your mass isn't changing, delta P is the same as m delta v. So this would be Dan's mass times the change in velocity for Dan, and that's got to be equal to the negative of the skateboard mass times the change in velocity for the skateboard. And I'm interested in finding Dan's final velocity. Well, in order to do that, I first need to find the change in Dan's velocity. So let me solve for that. Negative ms over md times delta v sub s. And here I can confirm my common sense reasoning a moment ago. How does the skateboard's mass compare to Dan's mass? 5 over 50 is 1/10. So I've just confirmed that Dan's velocity will change by 1/10 of the skateboard's change in velocity because Dan is 10 times more massive than the skateboard. And here's where I can say delta V for Dan is negative 1/10 of final velocity for the skateboard is 8 meters per second minus an initial velocity of 4 meters per second. So that's 4 divided by 10, that's negative 0.4. So just as I expected, the velocity will decrease by 0.4. Now, delta, that's final minus initial, right? Velocity of Dan after minus velocity of Dan initial is negative 0.4. So in other words, V Dan at time 2 is V Dan at time 1 minus 0.4 meters per second. And here's where we plug in the 4, because they were both going 4 meters per second. And there's the answer we expect, 3.6 meters per second. So that's one way to start the problem. If you like, maybe you're more comfortable with the other way of thinking about it. You'd like to say, actually, total momentum at time 1 should be total momentum at time 2. Now, technically, I should really have a subscript x because I'm talking specifically about x momentum, not y momentum. But since this is a one-dimensional problem, I'm not going to mess with that. So we would need Dan's momentum at time 1 plus skateboard's momentum at time 1. Even though these might be changing individually, their sum should not change. Dan after and skateboard after. Whatever total momentum is present before should still be there after. M Dan, V Dan at time 1 plus M skateboard, V skateboard at time 1 equals M Dan, V Dan at time 2 plus M skateboard, V skateboard at time 2. This seems a little more tedious, doesn't it? There's more subscripts to write. Well, here's where I can factor out an MD here and here. So MD times, now let me do this. Let me put all the skateboard stuff on the left side. M skateboard times VS1 minus VS2. And on the right side, I'll put the Dan stuff. V Dan 2 minus V Dan 1. Doesn't this say, well, this is initial minus final, which would be the negative of final minus initial. So this is actually negative MS delta VS. And over here, we've got MD delta V for Dan. This equation is identical to this equation. Didn't mean to cross that out. I meant to underline it. So of course, you arrive at the same place. And how you proceed algebraically is up to you. You don't actually have to factor out the masses and do it this way. You could plug in numbers here. So you do what works for you. Just make sure that you label your work clearly so I can follow it. And we're done with that problem. Now, do we need momentum conservation to solve this problem? Could you have done this problem a month ago? You've known about F equals ma for quite some time now, and I just maintained that there's no new physics here. This comes from F equals ma. Well, you could do it from F equals ma, but you would have to be clever about it. You'd have to apply calculus. That's the nice thing about using this starting point. Where's the equation I'm looking for? The nice thing about using this starting point is that the calculus has already been done for you. We already did the integration with respect to time and developed the equation. No need to rehash all that. Just go forward with this new problem-solving technique. But you could say, okay, I'm trying to do this off the top of my head, so we'll see where this goes. Let's look at Dan, and I'll say that the acceleration of Dan is the net force on Dan divided by Dan's mass. And I know that the change in velocity for Dan, think back to early in the semester, the change in velocity is the area under the acceleration curve. Okay, so I'd have the integral of the force on Dan over mass of Dan with respect to time. I could pull out the 1 over m. That's 1 over mass of Dan times the integral of force on Dan dt. And here's where I can recognize, let's see here, I'll draw it off to the side here. It's a silly idea, but or silly picture. Use a sphere to represent Dan and a sphere to represent the skateboard. The skateboard pushes on Dan via the friction at his feet. This is the force of the skateboard on Dan. And then Dan pushes on the skateboard with friction on his feet, or between his feet and the skateboard. Okay, so what is the force on Dan, the net force on Dan? Well, the only force I see is the skateboard pushing on Dan via friction. So here's where I would insert that. I'd say, let me give it a minus sign. This is negative magnitude of the force of the skateboard on Dan. Okay. But Newton's third law tells us that these are equal and opposite. So the magnitude of the skateboard's force on Dan is the same as the magnitude of Dan's force on the skateboard. This says ds. So I can just swap the magnitudes there. Let me pull out the minus sign. That magnitude is the same as the force of Dan on the skateboard. Where am I going with this? Where I see where this is going now. I'm going to use Newton's second law now for the skateboard. Remember, F equals ma. So if I know the net force on the skateboard, I can set that equal to the mass of the skateboard times the acceleration of the skateboard. This is the net force on the skateboard because Dan is the only force on the skateboard. So I'm going to set that equal to the mass of the skateboard times the acceleration of the skateboard. I'm integrating with respect to time. This is a constant. I can pull it out, negative ms over md, and I'm integrating the skateboard's acceleration between those two times just before he jumps off to just after. And once again, back to early in the semester, what is the area under the acceleration curve? That's the change in velocity. But this is the skateboard's acceleration. So I've just found that this would be the delta V for the skateboard. Don't forget what was on the left side here, the change in velocity for Dan. That's negative ms over md delta V for the skateboard. Aha, all I've done is rederive conservation of momentum. Take this md, put it over there, and you've got change in Dan's momentum is change in the skateboard's momentum. No new physics, people. But who wants to go through all this garbage every time? It's kind of cool to recognize you can do it, that you're really just using F equals ma and the fundamental theorem of calculus. If you get all this, you have a more mature understanding of this than I did when I took this class, and even for several years after I took this class. It's only after teaching this over and over again that you start to see all this stuff and how obvious it is. So you might as well just start from the conservation principle. We'll do some more problems in future videos.